Yes, we need a new GC. This promises to be a lively discussion afterwards. So, Stephen, Amaury, take it away.
All right, so as the title says, we need a new GC. I'm Steve Schveighoffer, and that's Amaury.
Yep.
Séchet, and we have been working on this garbage collector. The current GC, it's okay. It's based on the same code that's been in D1 since the Tango days. DRuntime is actually a port of Tango. We've had several improvements since then. Precise scanning was added a little while ago, but it was only really important for 32-bit systems because you can actually have memory pinned by a random integer somewhere in a stack. So with 64-bit addressing, it's pretty much no longer important. The fork scanner basically was created by, I think it was Leandro, but it was used by Sociomantic. That's also now an option that you can set but with a config flag. And the default scanner now is actually multi-threaded. It'll create a bunch of threads to scan your memory while this world is stopped, and that uses the CPU a little bit more efficiently. But those are basically the big improvements that we've had. It's not optimized for the architectures we have today, so there's still, anytime you look up where's a piece of memory you got to mark, it does a binary search for that piece of memory. There's too many touches of various pages. Anyone who's familiar with CPU architecture, Amaury is going to talk about that, is going to know that anytime you touch a piece of memory that's outside your cache, you're going to flush the cache and have some problems there. And yeah, it doesn't take enough advantage of modern hardware, and the TLB is something that we're going to discuss later, but does not try to reduce that pressure. All the allocations are done from a global structure, which means we need a global lock. And the global lock means that if you have multi-threads all allocating all at once, you essentially have a single-threaded application, which kind of stinks. You can't do any allocations while collecting. The problem is because of the global lock. You would have a deadlock if you did that. All threads must be stopped during scanning except for with the forking allocator. So if anyone's not familiar with the forking allocator, it forks a copier process. All the pages become copy on write in the second process. And then it just resumes your original process, does all the scanning in the forked process. Anytime a page is written to in the forked process, it has to basically stop both processes, adjust the page table, and then continue on. So you have these write barriers they're a little bit expensive, but at least you can continue running your application. And then once the scanner's done, it transmits all the dead blocks back to the original, and it can clean those up. Even doesn't have to stop the world for that even, I don't think, because it's all garbage anyways. The implementation is very tied to DRuntime, so all type data is fetched from TypeInfo. You know, we've had the talk about converting DRuntime hooks to templates, and that's a huge benefit because we don't have to rely on TypeInfo. You know, we can build functions that do specifically exactly what we need, but the garbage collector requires you to pass in TypeInfo for finalization and other things.
Okay, if I may interject quickly on that one, so that you realize how bad it is. When you allocate memory on the fast pass, that is taken like 99% of the time, half the time you spend is not allocating at all. It's just like fetching data from TypeInfo and other stuff like that and combining them in the right way to figure out what type of allocation you want to do. It's half the time. It's crazy. Like a template could get all of that at compile time and we win. Like we have a 2x on allocation performance right there.
Yep. And also the array runtime is dependent on implementation details of the GC, which I'm working on getting rid of. Who here has done like, oh, this GC allocation is bad, so I'm going to use malloc and free and save some time? Yeah, pretty much everyone. Most people use the C allocator as a faster allocator, but it's just an allocator, right? We should be just as fast. If you use the C allocator and you store pointers to GC memory in there, you have to pin that memory. Otherwise, it might accidentally get collected at some garbage collection cycle. We should be just as fast. And here's a few examples of things in Phobos that use cmalloc and pins the memory in the GC. And remember, pinning memory in the GC also has to take the global lock. So it shouldn't be faster. It shouldn't be faster to allocate with one allocator and then call into another allocator to pin it, but somehow it is. So that's kind of the de facto solution that people have reached for, but we should get rid of this so that instead of, if you want to do manual memory management, sure, just use the GC that's performant and malloc and free, and you should be fine. But because that is slow in the current GC, people don't do it. We're hoping to fix that. The GC that we're working on is only for 64-bit architectures because we take advantage of all the features that 64-bit addressing has. The current architectures that we support all use maximum 48 bits for addressing, which gives you a maximum RAM size of 256 terabytes, plenty of space. Using memory mapping, we can plan out how things are laid out so that we take advantage of these architecture features. We can use sparse data structure, so use a lot of address space, but most of it is zeros, and we're going to talk about how that works.
All right, so we're gonna, like, before we dig into the GC itself, we're gonna talk a bit of, about all the OS and the CPU managed memory, because a lot of design decision, depend on that, and if we don't explain that, then nothing makes sense. Actually, on a modern, and by modern I mean like at least, it's been true for more than 20 years, right? Like any kind of CPU that you used a variation of that scheme where a pointer is not like an actual address in memory, right? It's a virtual address, and in some way, it's kind of like a struct with a few fields, and then there is a data structure in memory that the OS maintains, that the CPU understands, that tells the CPU how to translate those addresses into physical address into your RAM. The way it works, at least, so this one is like for x86, 64 bits, but every single kind of CPU out there is going to use a variation of that scheme. The way it works is that, so first, the first 16-bit are going to be always 0, except if you do kernel development, they can be 1s, but we are not doing a kernel GC, right? So in our case, it's always 0s. And then you have a series of 9-bit buckets, and each of them are like an index into some kind of data structure to resolve what the actual physical address in the physical RAM is. And then the lower 12 bits are just like within the page, where are you, right? So the lower 12 bits are actually always the same between physical and virtual addresses. So the data structure that the CPU uses to do that resolution is effectively like a tree, and each level in the tree is like one page of 512 pointer like kind of thing. Those like are either gonna point to the next level in the tree, or they are gonna point to a physical address, right? And there are a few bits in there to indicate, well, is it a page or is it the next level in the tree? Is it readable? Is it writable? Is it executable? This kind of information. And so you end up with that structure where if you use like 4 level in the tree, you end up with the 4 kilobyte pages that I think most people here are going to be familiar with. This is the default that most system uses. But what you may not know is that those systems also support bigger pages that are going to be, like 3 level or 2 level in the tree. Like if you have the right flag that say, oh, this is a page now, then you're going to have a 2 megabyte page, 1 gig, or like 512. I've never seen anyone use that, but in theory, if you have enough RAM, at least it's theoretically possible. So you're gonna realize, like for instance, if you branch out at level 2 and have a 2 megabyte page, well, the 9 bits level 3 here, they are just like part of the, they join the 12 bit here, and they are part of the address within the page. So now you have a 2 meg block that is 2 megabyte aligned, and all of that is within the page. So why this is important is because this whole process of resolving addresses, you can imagine, is like pretty expensive, right? If you had to do it every time you do a memory operation, a store and a load or whatever, you had to like walk down the tree, which involved itself, like 4 loads pretty much. Each one of those loads can also be a cache miss, right? So potentially that's pretty expensive. And your MMU is doing that to resolve address. So there is a cache that is similar to the L1 cache you have for instruction or data in your CPU that is called the TLB, that store the result of that process, right? So if you access the same page several times, well, the first time it's gonna have to do that resolution, and subsequent time it's gonna, fetch the result in the TLB, and it's gonna give you like the right physical address right away. So you don't need to do it like many, many times. But just like your L1 and your L2 and stuff like that, the TLB has typically different level, but the one that is fastest and very close to the CPU is very small. And so as program got bigger and used more and more memory, it actually becomes a problem to work with only 4K pages because, in a modern application that's going to use several gigabytes of memory, the number of 4K pages that we represent is like way, 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 way bigger than any space that you have in the TLB, right? And even the hot set of data that you access a lot, it tends to not fit in the TLB anymore. You want to be able to leverage at least those 2 megabyte page, as much as you can. And it's very important in the modern age. Like for 32-bit system that were pretty small, it doesn't really matter. But know that we have, big application with a lot of memory, justified or not, we can discuss that. But this is, how things are now. So we want to be able to leverage those 2 megabyte pages as much as possible. To do that, the OS is actually going to help you because all modern OSs, maybe if you use like embedded stuff and they may not support it, but like, Windows, Mac OS, Linux, the big usual suspects are all going to support the feature that's called transparent huge pages. And what it says is like, once you request memory from the system, it's going to give you some, and it's going to be split into 4 kilobyte pages. And as you use it, the OS, may notice, hey, here we have a consecutive 2 megabyte block of 4K pages that is all used by the application. It's 2 mega line. I can swap that out from behind the back of the application into a huge page. Previously, you would need 512 entries in your TLB to represent that whole thing, and know that the OS shifted it to use a huge page. It's just one entry, right? So when the OS can do that, it's effectively a multiplication by 500 of the size of your TLB for the specific chunk of memory. Obviously, you cannot do it for everything in memory, so in practice, it's not a 500x, but when it can do it, it's literally a 500x improvement. So that's a pretty big deal. And modern OSs, they do that behind your back once in a while, and you can also hint them. For instance, on Linux, it's going to be with the madvice function or memory advice. I'm not sure how we say it, but that function can hint the OS like, hey, you might want to look at this and turn that into a huge page. But even if you don't hint the system, it's going to try to do it behind your back. Another concept that we need to explain, because we leveraged it quite a bit in various places, is the concept of like virtual 0 and O that is memory mapped by the OS for you. So when you request memory from the OS, you actually don't get any memory. You get address space. And as long as you don't write to it, there is pretty much no memory there. You can read zeros from it. It appears to be like actual memory that you can read from, but it's not. And the way it works is that it gives you effectively like a degenerate page table where it all points to the same zero field page that is write protected, right? So if you read like any address in there, you're gonna resolve all the level, but like whatever you are in the first level, you point at the same place in the second level, and whatever you are in the second level, you point at the same entry for the third level, and so on, right? And at the end, you point to the same write protected zero page. This is very useful for us in many ways that we're gonna describe in the implementation. But generally, because we are the allocator, we cannot rely on an allocator to allocate for us, right? Like that's, fairly obvious, right? Sometimes we're gonna be like, oh, we don't know many of those things we need, right? Maybe we need like 1, 2, 1,000, we don't know, right? So what we do in those instances, it's like, well, reserve the address space for the maximum number that we think we can need. And as we use those zero pages are going to be materialized on, as per needed basis. And we don't use that much actual memory, even though we use a fair amount of address space. This is a bit of a diagram that demonstrates like what happened when you write somewhere in there, right? That zero page is zero protected because the OS is pretending for you that there is an actual huge chunk of memory there, even though there is just one page full of zero. So when you write in it, the OS traps your write, right? Because the page is write protected, so you get some kind of fault and the OS can catch that and do the right thing. And what does the OS do? Well, it creates a new path, here represented in green with the red arrows. And, your new page, it's gonna like locate a new page for you where you can write in, and everything else still point to the magical 0 page, right? And as you start writing into more and more pages, more and more of those green paths are being created in the page table of your operating system to do as if you had a bunch of memory there all along, but you did not. And this is why if you look, with tool like htop or whatever, if you look at the statistics of your program, you're gonna see like how much memory does it use, quote unquote, and it's not really memory. You want to look at how much resident memory does it use, and it's not gonna be the same value. The resident memory is gonna be smaller, and the resident memory is actually like how much green stuff you have here, like how much like real memory there is with real RAM behind it. Whereas the total memory, it's gonna be actually the address space, and a lot of it is gonna be, or a little of it depending on the application, but some of it is gonna be just like virtual zeros. So we rely on that mechanism quite a bit because effectively, like, we can use the operating system as an allocator for us when we need it that way.
Now we're just going to go into the first part of how the GC works. So we're just going to discuss large allocations this time. One of the cool things that we have in our GC, we wanted to create our own mutex to avoid initialization of our allocation. Like Amaury said, we have all 0 data. So as long as you have something that's initialized with zeros, it's free until you use it. We don't want to have to allocate memory for our mutexes. We don't want to have to initialize with anything with zeros. So we have these mutexes, and we don't have to actually initialize them in anything. So we may declare large amounts of metadata structures. As long as they're all zeros, it doesn't actually materialize, so it doesn't cost anything. We're not contended, so atomic operations are enough to take the mutex. So if you don't have multiple threads going after it, it doesn't matter. It's really fast. And even under contention, we just swap out to using a kernel API. The region allocator is the main piece that gets data from the OS. So the region allocator gets allocations 1 gigabyte at a time. Remember those 1 gigabyte pages, but of course they're all zeros. At the beginning, you just ask for 1 gigabyte and it just gives you 1 gigabyte of memory, but you still only have, just a page table in your process. We track ranges of memory that are not used in a red-black tree, and we have 2 separate regions, one for pointer-containing blocks and one for non-pointer blocks. And this is important because we only want to scan the pointer-containing blocks. So if we section those off in its own address space, we can both easily determine if it's pointer-containing, and we also keep that scanning algorithm so it's focused on the same part of memory. Once the region allocator gets its 1 gigabyte of space, and it can ask for more if it runs out, it's going to hand out those chunks in those 2 megabyte pages. So it's important that we use the right sizes that the operating system likes.
More like the CPU.
CPU likes, right? The things that the region allocator hands out are 2 megabyte pages. There's a thing called a page filler. I guess this is a standard term. It confused me when I first read it, but
this is the term from TC malloc. So we just, went along with it.
So the page filler gets its address space from the region allocator saying, give me a block, I need n blocks, whatever. Of course, we have 2 region allocators, so pointer-containing blocks are separate from pointer-free blocks. They're tracked in heaps, ordered by the longest free range and the number of allocations. We have all these heaps. You'll see the diagram later. We have some small allocation heaps, which we'll talk about in tomorrow's talk, and large allocation heaps. Basically, each heap is sectioned off by allocation classes, which are basically, if we wanted an allocation of like 15 pages, there's a certain heap for that, either that or bigger. So the longest free run of memory we can pull data out of, we put it in a heap. We store, I guess it's 31 heaps, right? Not 32. So
this is 31, yes.
Yeah, so that's a typo. But anyways, since it's under 32, we can have a bit mask that basically gives us a constant detection of which heap we should pull from. So with one operation, we can determine exactly where to get the next piece of memory from or allocate a new block. As a result, heap operations take amortized constant time, and we'll see how the heaps work in a minute here. A little note on metadata tracking. In addition to the memory you're requesting for your application, the allocator also needs some tracking data, just kind of like the OS needs a page table, we need to track this data. So we have some allocations that basically never get freed, but they're metadata, and then when you stop using them, it just goes on a list of unused ones so that you use it later. The main thing here is the block descriptor, which keeps track of just various information about the block, how many pages in the block and which pages are allocated. Remembers the longest free page run, which is used for sorting the heap. Allocation class, which is like a range of free page lengths, which we have a list of those later. How many allocations are in the block, so that's just for like bookkeeping and stuff like that. And then a generation. As you ask for more data from the region allocator, it stores which generation. So like you ask for 1 gig, oh, you ran out of that, you need another gig. So that's generation 2. And it tries to keep those blocks together, or those block descriptors together, so that, again, we're trying to keep things as close as possible so that you're not touching multiple pages of memory that then it's going to flush the cache. Unused metadata, like I said, goes into a heap to be organized by the generation so you can use it later. The pairing heap data structure. This is a cool thing that we took from malloc.
malloc, yeah, but malloc also took it from elsewhere. It's
so
very old arcane technique that were a bit lost at the time and rediscovered in recent years.
So if anyone's familiar with a heap, basically a heap is a tree, kind of a tree structure that has the most important value is at the top. So you're always looking at that one to be the next one that you want, and then once you remove that, it does some amount of operations to put the next best one at the top. When inserting a child, is it better than the root node? If it is, then it becomes the new root, and it's just like a linked list. It goes to the next one. If it's worse than a root, it goes into kind of an auxiliary heap off to the side. Whenever a child is added to the auxiliary heap, if the count is even, then we perform n merges, where n is the number of trailing zeros. And in practice, that it amortizes to 1 merge for insertion. So if you have like, okay, 2 insertions, I do 1 merge. Then I have 4 insertions I'm going to do, like 2 merges. So
and you do 8 and you do 3.
3, right? So eventually it ends up being like close to 1. I think like 1-to-1, right?
It's going to be 2, right?
2,
like
2,
you,
1.
well, you have to insert your node,
yeah,
and then you have to merge 2, and half the time you do 1.
Yeah.
A quarter of the time you do 2, 1/8. So it's like half plus a quarter plus 1/8, and so on. It tends toward.
It approaches 1.
It tends toward 1, so total is 2. So you do, on average, 2 merge operation or insertion. So it's amortized constant time, which is pretty cool.
So when we remove the root, then it performs a merge on the root's children, which is generally like 1 to 2 children, and it performs a merge of the new root with the auxiliary list root. We're going to show a demo of this. I wrote a little application to kind of show what it looks like. First, I'm going to put things in inverse order. So you have a node at the top. That's the root node. It's got a value of 127, so lower numbers are better. So I'm just going to add nodes, and as I add nodes, it just becomes a linked list because the new node is always better than the root node. And then if I pop them off, they just come off in that order too. You can see the comparisons done and the operations. So the comparisons are way less, so it's actually better than standard. Now, if I reset this and put like random values in, and you'll start to see this is the auxiliary heap to the side growing off, and we just keep. It kind of looks like a binary tree, but it's like off to the side. But you can see the comparisons are about twice as much, and as we pop off, they become a lot more. But it's still amortized constant time essentially. Now, if I do this in
you might want to do this in reverse. Yeah, this way. So that we show the auxiliary list, or it builds up.
Yeah. So if we do this this is like the worst case. Every single time the new one is not better than the root. It just keeps filling up the heap here, and as we pop them off, it actually is pretty fast. So this is just like a little demonstration of what it looks like if you can visualize. I think it's a lot easier to understand.
All right, so we talked about allocation classes a bit before, and don't worry, we're introducing many concepts. We bring them back together in a bit of a diagram, as we explained, but we need to explain a bit the fundamental components before we put them together. To try to allocate large allocation, it's going to be on a page granularity, right? So it's going to be on 4K granularity, effectively. We allocate those large allocation from blocks, and we are going to sort, essentially, those blocks into different buckets. Each bucket is going to be a heap, like he demonstrated, based on what is the longest free run of pages in that block, right? So that we can know, hey, if I want to allocate, I don't know, like an allocation for 12 pages, I need to go into one of the heap that has blocks with 12 pages free or more. Because there is 512 pages in a block, we don't really want to have 512 buckets. There are two reasons for that, but the first one is just because that's a lot and that would just take a lot of resources for no good reason. Like most of them would be empty and the vast majority of them would have one element in them. We essentially use like different sizes with 2 bits of precision effectively. So for the smaller one, it's going to be the exact number of pages, but as it grows, after 8, it's going to be like 10, 12, we go 2 by 2, and then we got 4 by 4, 16 to 20, 24, 28, 32, it's like 4 by 4, and then 8 by 8, and so on up to 512, which obviously we never reach because if the block has 512 pages free, then the block is empty and we return it to the region allocator. I don't know, if you've programmed for quite some times, you've seen like all those numbers, they're a bit usual suspect in programming. Those are, kind of like recurring number that you're gonna stumble on, all the time. And those are what we use as our allocation class. Say you want to allocate like a large allocation that's gonna take, say, 21 pages. Well, you need to allocate from the heap with like 24 pages or more of free run, because the other one are going to be too small for you. And you're going to have to select a block in there, and you can do your allocation from that block. So now the question is like, do we actually want to do best fit? Because it's a bit wasteful, right? If it's 21 and we do at best 24, maybe there is a block somewhere that has 22 pages free. It's going to be in the 20, bucket. And we're never going to use it to allocate our 21 pages allocation. So the question is like, is that a problem? Is that wasteful? And like to some extent it is, but there are 2 good reasons to do that. The first one is obviously we can do the lookup much faster in this way, and that matters as well. But more importantly, what people realized over the years when building memory allocator is that best fit is actually not the best, right? So intuitively, when people started building allocator, they were like, okay, let's sign, if I'm looking for 21 and there is a 21 range somewhere, I want to use that. And if not that, then a 22, right? And I want to be as close as possible. The problem with that approach is that you end up with a lot of very small runs of pages, like 1 or 2 pages, and you don't have enough demand from the system, in other places to fill all those very small runs. So having some amount of slack is actually beneficial. Too much is also going to be, not good. But you want like mostly best fit, but not quite. That's what is actually best in practice. That's 31 allocation classes in total, and it's pretty much how it works. So then we have page filler. Steven talked about it a bit, but we're gonna dig in there a bit more. So there are 496 of them potentially, right? Because they're all virtual zeros. So when we start using one, it's gonna materialize, but all the other ones are just, static address space that we take, but there is nothing there. Why? Because we cannot dynamically allocate them because they're the one doing the allocation, right? So when we need a page filler, for instance, to do a large allocation in our case, we're gonna select one. How do we select one? We use the ID of the core you're running on to do that, right? So if you have 4 core machines, it's gonna end up using like 4 different page filler, and depending on which core your thread is running, it's gonna pick, the corresponding page filler. Why do we do that? Well, that's a way to ensure that there is very little contention, because the only situation when there are gonna be contention is when the OS, suspend a thread that is mid-allocation and, resume another thread on the same CPU core. And that other thread is going to also do an allocation, right? And that requires a timing that is quite specific. That is still possible, and this is why we use mutexes in there. But it's like very uncommon in practice, so we get very low contention without that mechanism. As we mentioned, the page filler maintains a set of heaps for each allocation class to be able to select the best block that correspond. This is a bit of a simplified diagram of how it works, but here you have the page filler. You have 31 heaps that corresponds to each allocation class that you may need. And you have a bit field that contains 0 if there is no blocks in that heap, and 1 if there is some block in there. No, imagine you want to do an allocation, and based on the size is allocation. It's allocation class 5 or more that you need. Well, you're gonna build a mask that have the first 5 bits are 0, and then all the following bits are gonna be 1. You mask with that. You count the number of trailing 0, which is 1 instruction on modern CPUs, and boom, the index of the heap you need to get from. Right, so it's like a couple of instructions, quite literally, to know which heap you need to pop from. And then you pop from the heap, and we've seen that this is amortized constant time. So we can select the right block to allocate from, basically in amortized constant time. We maintain the list of all the blocks, because when we do like garbage collection process, sometimes we need to go like over all the blocks that we've allocated in there and do some maintenance work. We're gonna dig in that a bit, but it's more for tomorrow. Now that we have all of that, we have all the pieces that we need to allocate a large allocation. So what is a large allocation? Is like more than 14 kilobytes, right? Because at this point we get into page granularities. Okay, smaller than that, you need to be, you need to maybe like fit several allocation on some pages because you start wasting a lot of space. But after 14K, we consider we are fine. So based on the size of the thing, we compute the allocation. We compute the allocation class. Based on that, we select the heap and we pop from the heap the block that we want there. Once we've selected the right block, we select like a number of pages in the block, and we create what we call an extent that describe, hey, there is an allocation there. It's that many pages long. If it has a destructor or stuff like that, we also put that in the extent. Basically, the extent is like a structure that describe, hey, like here is your large allocation. And here is all the property that this allocation have. The extent is 128 bytes in size. It's gonna come important later because we can 128 byte align them. That's pretty much it. Very simple data structure. Gets more complicated for small allocation, but that's gonna be for tomorrow. Just like block descriptor, those are allocated but never freed because they are managing allocation, so that's difficult. So when if you free a large allocation, they'll return into a heap of unused extent, and next time you need an extent, it's gonna pop from there instead of allocating new ones. So in practice, it's not a big deal. Okay, for huge allocation, because we've seen we allocate from blocks, but blocks are 2 megs. What if we want to allocate a 4 meg large allocation, right? Like what do we do? When it doesn't fit on blocks anymore, we call them huge allocation because huge is bigger than large. So, basically, what we do is that in that case, we don't use a block because we cannot. We request from the region allocator a set of contiguous block where we can put that thing in. If it's not a multiple of 2 megabytes, for instance, you ask for 3 megabytes, well, there is still 1 megabyte free at the end of the last block. So that last block, we're gonna give it to the page filler to, to put something after your allocation. We tend to deprioritize those blocks. So in each heap, we have a priority system between blocks to know which one are the best to take from and which one are not the best. And one of the parameters that we use is how many allocations are there in that block. Not how many pages are allocated, but how many allocations. Why do we want that information? Well, because if there is, if you did like a 3 megabyte allocation, half the block is full, but with just one allocation. So there may be like just one free somewhere that frees up the whole block. Right? Whether if you have half the block that is taken, but with like allocation that are 1 page in size, you have hundreds of them, and the probability that those hundreds of them all go free at the same time is pretty low. So if you have 100 of them, de facto your block is immortal now, right? But if you have like 1 or 2 of them, there are good chances that the block is gonna go away, right? So you want to target the block that are statistically likely to be immortal rather than the one that you're going to be able to be free later on, right?
When we want to find what block or page or information about an address, we maintain a 2-level radix tree for reverse lookup. So you get a pointer, you want to know the metadata about that pointer. We have this 2-level tree. Level 1 is a 2 megabyte buffer of static data, initialized with zeros like everything else. Each pointer size thing in that is pointing to the next radix tree bucket. So that first level never goes away. So we require it at the beginning of the application. We need this 2 megabytes. Of course, it's still zeroed address space. And in practice, that doesn't get filled up very much anyways, because each level 2 is made up of another 2 megabyte buffer, and that covers a gigabyte of actual address space. So unless you allocate, you use 1 pointer in the first level, for 1 gigabyte of address space. So you're not gonna do probably more than 3 or 4 of those most of the time. So it's actually pretty efficient. The whole data structure is lock-free and can be accessed by multiple threads at once, so we have low contention on that. And this is kind of a model of how it looks. You have your pointer, you have 16 bits of used because we only use 48 bits in the pointer. The lower 12 bits are also unused because those are per page.
The address within the page, yeah.
Yes, address within the page. We have 2 18-bit things. Each one is 2 megabytes. So you have 2 megabyte pointers to table 2, and then various table 2 descriptors that would be composed of these page descriptors. Each one of those tables in the level 2 covers 1 gigabyte of memory. And this is what a page descriptor looks like. We get 4 bits indexed into the extent, which is important for small allocations. We'll see that tomorrow. Arena index, which is which of those page fillers are you using? The extent metadata address. So this is the pointer to that little extent thing that's 128 bytes. So this is why we have 128 bytes aligned. The lower 6 bits is what kind of an extent it is. If it's a large extent, the extent class is 0. If it's something else, then it's a small extent, and that's, again, for tomorrow. And then we get 1 free bit. So we have room to grow this data structure at least once. All right, so when you want a free large allocation, use the radix tree to find the extent, the block, and the page filler. So you get all that information just from that tree. So it's basically 2 lookups in memory. We clear the page description from the radix tree. So we remove that element, and we remove the block from its heap, and then we free the pages, and then we reinsert it into the appropriate heap. So you've freed this piece of memory. It might change the class, the allocation class it goes into. So it could go in a different heap. It could get completely freed. All that stuff happens at that point. That's freeing a large allocation, and I guess we've got to the end then. Tomorrow we will be talking about smaller allocations, because most people are not allocating page size things. You're allocating a few bytes here and there. So
yeah, smaller and collection.
Yeah, and collection. Yeah, that's important too.
So you talked about huge pages, and one of the problems that we have with the optional flag for using fork, we can't actually do it because huge pages doesn't copy on write on Linux, so we can't do that. And also parallel GC, I think we disable it for some specific reason. I don't really know. So GC is particularly bad for us in that regard, because we don't have this advantage. A few other things that I have some ideas also for the GC, so I can share with you. For example, one of the things that I've seen from the first like our current implementation is the page size is locked to 4K. And for example, for AARch64, the kernel can be configured to use 64K pages. So the page pool of the GC is actually not using a lot of space. Maybe we are losing a lot of memory because of that. If someone can actually take a look at it, because I tried to look at it, but it's very not documented. So it's if someone wants to touch there and not break anything on the GC, would be cool.
So I won't be able to answer the question, but on the large page, 2 megabyte pages, the reason why it performed very poorly with the fork is because every time you write into some piece of memory, it's going to do copy and write. And obviously, if you have 2 meg pages, then the OS have 2 choices, and the 2 of them are bad, right? So one is you copy the whole 2 megabyte page, right? And you duplicate that, which is going to create like a lot of mem copy going around and a lot of memory consumption. The second one is like you split back that page into like 4K, and you clone the one that is 4K, but that require modifying the page table, which is also expensive, right? So when you do that with the fork technique, you're a bit in a catch-22. We have a strategy for concurrent collection that we want to implement like in the next version of that thing, because we cannot do everything in V1, but we have a good idea of how we want to do it, and it's a bit different than the fork, for that reason, amongst others. Also, the other remark was based on the fact that ARM, 64-bit ARMs use different page size, and it's actually a bit of a mess because it can use like 4K, 16K, or 64K pages, right? And it's gonna depend on in what mode the operating system configure the CPU. So it's a bit complicated. We are not the only ones having problem with that. I've talked with various people working on other memory allocator as part of that process, and it's always a bit complicated. But what most of them do is that they keep using 4K pages as granularity anyway, even though the system is gonna fill 16K every time. But for the block size, they may use 32 megs, for instance, if the system is configured as 16K pages. And I don't know if it's 64K pages. I don't know what the next level pages size is, but it's probably something like absurdly big. So I'm not sure it's worth doing that, but 32 meg block could be an option on those systems. We're gonna have to try.
I think it's half a gig is the next size.
It's half a gig, yeah. Well, the problem, like if it's get to half a gig, it's gonna be very difficult to fill consistently, right? Like you're not gonna get half a gig of different allocation with no holes in it consistently. It's going to be very, very difficult for the allocator to create that situation.
I noticed that on one of the slides, you track whether the pages are dirty. Does it mean that you have write barriers?
Which one was that?
It was earlier in the presentation. One of the points was that you were tracking if pages were dirty. I think that's something you want to do if you have write barriers, and I wanted to ask if that was something you're doing.
I see what you mean. I'm not sure what slide you're referring to, but I understand the question. There is a very sad story there. It's a very tragic story because in the page table, there is a dirty bit, and the CPU fills it for free, right? The problem is this is accessible to the OS, and the API that exists on different OS to check that information. First, they are non-standard. They're going to be different for every single one, and they are all complete and utter garbage, right? So, so what many people end up doing is like re-implementing a red barrier on top of it, even though the CPU gives it for free. If I had a lot of power in this industry, I would badger operating system implementation so that they give us a good API, but I'm afraid, I'm not that powerful yet. So we're gonna see.
Each architecture has a slightly different way of doing that, right? So you don't get all the other CPU architecture folks all in the same room and doing the same thing.
Have you tried using page faults to track writes as write barriers?
This is the plan if the fetching the dirty bit with the Cree API doesn't work, or we don't have it for that implementation. The problem is like it's way more expensive to do it that way, but you can disable it, right? So it's a like one-time cost, and also we can limit it to only the memory region that contain pointer. You don't really care about writes, of memory that don't contain pointer. So this is one of the reasons we segregate the memory. Like what I'm talking about is not implemented, but the reason we've implemented things in a certain way is so that we can implement that in the next version. Doing memory protection on the memory that contains pointer and tracking the write there is definitively in the cards.
I wanted to ask questions about the architecture differences, but I think it sounds like you guys are just using mapping 4K pages as if just slicing up a huge page or a 64K page on AR64. You guys are just going to slice that into 4K pages?
Yeah.
Okay. The other two questions were on the best fit versus first fit or other kind of approach. One approach I've seen is when pages become scarce, and I don't know if we actually know that pages are scarce. I don't know if we're actually interfacing with the operating systems enough to know, like memory might be low, but if then you could shift your approach. So you willing to pay more to try harder to get a page in the face of scarce resources. And I don't know if that's something you guys have considered or not, or if it's even applicable. Do you even know if memory is scarce?
Well, it's probably possible, right? Because you have application that gives you here is how much memory there is in the system, here is how much memory your program using. So like you can know, but the API are going to be non-standard across systems. There is a second drawback to what you're mentioning. So obviously it's going to be a bit more expensive to do best fit, but the problem with best fit is that it creates long-term fragmentation because you have like those, unless you have the exact size, right? You're going to have like a little extra, and you end up creating, too many of those little extra, and there is not enough demand for slices that small to fill them. So you create like long-term fragmentation in your heap when you do that.
So that's a nice segue into my next question, which was an approach I've seen used in other systems I've used. I assume you're familiar with the slab allocator, and one of the big advantages of the slab allocator, aside from being very, very efficient, is that because you have uniform sizes, and if you have fixed size objects, and I don't know in D how frequently applications are. I know in the applications I work with, we have a lot of objects that are pretty much the same size. So the slab allocator is a really nice solution for when you have that kind of a profile.
We're gonna cover small allocation tomorrow, but we use a variation of that idea for small allocation because it works great. Though we needed to cover large allocation first because what do you do to get a slab and to get like many units in it? Well, you do what we described today, right? you get like a few pages and you make a slab out of them, and then you allocate from that. So even though that's slab is more common, like in practice, you allocate small stuff way more often than you allocate large one, but we needed to explain that one first.
Actually, I forgot my question, but one thing that I wanted to answer for Garrett is we on the current GC from the code that I read, we basically check the memory usage and call the gc.minimize, which will basically defragment the pool of pages that we have. I don't know if this is just for large allocations, but also for small allocations, but I'm not really sure. But yeah, we definitely do that.
In the current GC, I don't think that it provides, so it doesn't give back memory to the OS, I think, until you call minimize, right? So like it'll just keep free things in a list.
It does, but not that much. Yeah.
So that's like the way it does with our allocator. As soon as we see that a block is completely free, we'll give it back to the OS. And so I don't think we need to support that piece, right?
Yeah. So we release blocks on a 2 megabyte granularity. We also, when you do a garbage collection cycle, but it's for tomorrow, it may be missing some pieces. But when we do a garbage collection cycle, at the end, we need to scan all the block to see all the dead stuff that are in there and free them. And as part of that process, if there is more than I think it's 64K in the block of memory that is actual memory that we've used but that we don't use anymore. If we are more than 64K, we purge all the unused page in the block. Now we want to have some slack there because purging that memory is expensive in itself. And so if you very aggressively purge everything that you don't use, you end up like purging the memory and then requesting it back from the OS when you start writing in it and so on and so forth. So we added a 64K slack in there, or 16 pages. So we allow basically 16 pages dirty, unused in the block. And if there are more than that, we purge everything.
Towards the beginning of your presentation, you said that you're trying to remove the need for TypeInfo when you are running your sweeps. My question is how? Because what happens is that the DRuntime will sometimes need to put those TypeInfos in there. For example, when it creates new structures or classes, in order for the mark phase to be able to correctly mark indirections. For example, if an object has references to other objects, then those should also be marked as live. So then how do you want to get rid of that? I would love to not have to write that thing in the runtime, but I don't see how.
So in my fork of DRuntime, I actually have removed the requirement to have TypeInfo because we need it for our garbage collector.
Okay.
It turns out there's two things we need from TypeInfo. For the precise scanner, we need the bitmap that comes from the compiler. It says these are the words that have pointers in them. And that's just basically a compile time constant byte array. So we have this thing called RT-info that takes every type and puts it into the TypeInfo. But the only reason it does that is so that it can then later use it in the garbage collector. We can just pass that block into the garbage collector. So that's one thing. The second thing is the finalizer. So if there's any finalization that you need to do, we pull that from the TypeInfo. You obviously still need the TypeInfo for classes, but we know that's in the block already. We don't store it separately. I'm still playing with the API a little bit, and I'm eventually going to submit a pull request to fix all that. But right now, I have it working without TypeInfo.
Okay.
And I think it's good not to have TypeInfo as a requirement because of the cost of calling the virtual functions in the class, and you're going around touching quite a few things that might not be cache local. So it becomes very expensive.
Yeah, the TLDR is everything you get from the TypeInfo, you could have known at compile time. And so you could have directly called the GC, like, okay, give me an allocation. It's this size. It contains a destructor or not. Here is what the destructor is if it's contained one, and it contains pointer or not, right? Like all of that you can provide at compile time and generate direct call to the GC with the right information.
With the new template runtime hooks, we're already using the compiler to tell, does it have pointers or not have pointers? Does it, those bits that gets sent in already are being done outside the TypeInfo. So we're not really using the TypeInfo as much. It's just for those two things.
So then the GC has to be compiled together with the code, right? Because you can't just use it in a precompiled fashion. Otherwise, it wouldn't have the compiled information, correct?
The GC just will accept, you have a list of, you have a bit, you have this pointer bit field. It accepts that as a parameter. And you have a finalizer function, accepts that as a parameter. So that's it. The runtime extracts the stuff from the TypeInfo instead of the GC itself.
GC malloc should become kind of like best practices for general allocation, that you just call that instead. Is there any downside to just migrating to GC malloc from malloc as a common practice in greenfield code? And the second question was with regards to your development environment. I think that you've surfaced a few portability concerns, and I was wondering what you're actually using. I think, Steve, are you on a Mac, like your Mac ARM or something? I was just wondering if you were already doing automatic kind of portability testing in your own development.
Currently in the DRuntime, it's not really the malloc that's terrible, it's the free that's really expensive. We're working on providing a faster allocator in that sense. You can use it now, it's just going to be not as fast as like cmalloc. It's okay to use it, just the performance isn't there yet. Until we get this new GC, and it's not going to be there. But yeah, eventually, hopefully, it just magically switches over to this fast stuff. So
there is something I want to add there. Yeah. So one of the design constraints of what we've been building is like if you use the allocation and the free function from the GC, you get a similar like memory and performance profile as you get from malloc and free from C. That's a design constraint, and that that is working for us. So if you free everything explicitly, you should get the same as malloc and free from the system. One of the big motivation there is that people use malloc and free, and then they pin and they do all this kind of funky stuff. But it always come back to bite you in the ass later on, because there might be pointer in there that you have not pinned or whatever. And we actually have a cunning plan of swapping malloc and free with our stuff. So that we can tell people like use malloc and free if you want, but it's gonna forward to that. It's almost working. There is one thing that is not working in that cunning plan. It is that when you start threads or when you start and stop threads, the threading library actually uses malloc and moves stuff around and reuses buffer, does some like crazy shit in there. The problem is like as part of the collection process, because we do parallel mark, we start thread and we stop them, and you need to get the sequencing of all of that exactly right so that you don't miss anything that is in the libc when it does this Chingian, with thread creation and destruction. And we don't have that part completely nailed down, but otherwise it's it's all good. So so that's the cunning plan.
Yeah. The GC that we're building is using SDC. It's all kind of SDC flavored code, and it currently only works on Linux x86, right?
Yeah, it should be pretty close to working on OS X though.
Okay. So, but we haven't tested.
SDC works on
the plan is for it to work everywhere though.
Yeah.
And it will probably end up
everywhere. At least the big suspect, like OS X, Windows, and Linux, right? Yeah.
There's many aspects of like making the system faster by having a more efficient allocator, and also one of the factors that goes in is how much are you scanning when you're doing your kind of your sweep to determine what to garbage collect? And as you guys mentioned earlier in the presentation, often the way programs operate is there'll be a few variables that live for the entire lifetime of the program, and then there'll be like cycles of smaller lifespan variables. Is it possible or would it be worth it that if certain blocks of memory keep surviving sweeps, that they essentially get moved to another tier that's checked less often so that each typical sweep is smaller?
So we actually have pieces of code to do that. Like we keep a generation in the block that tells us, essentially like how old it is. Right now, we are not prioritizing that because we've found that, prioritizing other stuff was working better. But I'm a bit like dissatisfied that we don't do more with that. And I think there is something there. I think you're right. There is something there, but we have not quite nailed it yet.
Tomorrow, are you going to cover anything around like telemetry that you're going to report back so that as an application, as a user of the garbage collector, we can see kind of what's going on, so we could see whether if we've invoked some pathological cases, that kind of thing, or is that a version 2 thing or that you thought about?
This is like how does it perform, you're asking?
Yeah, in Windows for .NET, you've got performance counters that tell you how many generations you've got, that kind of stuff, so you can see whether you're doing stupid things by accident. So is that sort of
currently
have ideas of what you might want to track and see, or how we could use that to feed back to for progress in future?
Yeah. We use a very fancy technique to do that right now, which is kind of like printf, except we cannot use printf because it allocates. But you can use snprintf to print stuff in a buffer, and then use write to write that wherever you want. It's not ideal, though. We actually need some telemetry at some point, but we don't have that at this point.
All right, now let's proper end it here. Thanks, guys.